So, good morning, students. Good morning to all of you. Welcome to the GATE lecture series, Prerana scheme sponsored by AICTE. Today, we will cover within 2 hours, we will cover the vibration topic. So, let us start the topic. I am just presenting my screen now. Okay, tell me, students, the screen is visible properly? Yes, screen is visible. Hello. Screen is visible to you? Akhilesh, Sanket, Vibhor,
Yes,
Harshal,
sir. Yes, sir.
and am I properly audible?
Yes, sir.
My voice is clear, so shall we start now?
Yes, sir.
Okay. Good morning to all of you. Welcome to the lecture series, Prerana scheme sponsored under the Ministry of HRD, Government of India, AICT. So today's topic is related with vibrations. So this in vibrations, these are the content that we have to cover today. Introduction to vibration, then the various terms used in vibratory motion. Similarly, what are the different types of vibratory motions? Then what is mean by longitudinal vibration, transverse vibration, and torsional vibration? Similarly, what are the various method of vibration analysis? For example, there is an equilibrium method, energy method, Rayleigh's method. So with the help of all these three methods, we will determine the natural frequency of a system. Then we will move to the transverse and torsional vibration. We will see how to find the natural frequency. Then we will move to the concept related to critical speed or whirling speed of shaft. And after that, we will solve or we will practice some gate numericals. Okay. So let us start. First of all, introduction to vibration. Now, basically, vibration is a phenomena where, and you can observe this phenomena everywhere in the society. You can observe this phenomena. It is a mechanical phenomena, and in simple terms, we can say that whenever there is an oscillation or whenever occurrence of oscillation takes place with respect to or about an equilibrium point, the vibration phenomena occurs. It is the study of repeated motion of objects. In this figure, the animated video, you can see that a pendulum is oscillating with respect to its equilibrium position. Continuously, it is oscillating towards the right or towards the left. So, whenever the position of the pendulum changed from the mean position, okay, to the right or to the left, the vibration oscillations will be developed, as a result of which vibrations will be induced in the system or a body. So this was an example of a simple pendulum. You can also take the example of a spring mass system. Similarly, the string instruments which produces sounds, with the help of vibrating strings. For example, your guitar. These are also the examples. Now, vibration have some good effects also and some bad effects also. First, we will see the good effects. In good effects, musical instruments, then vibratory conveyors, then shakers, then stress relieving equipments, hoppers. Similarly, the bad effects are unwanted noise, loosening of the machine parts due to the vibration, as a result of which excessive stresses are induced in the system. So, vibration creates rapid wear of machine parts. So, there are number of examples related to vibration where we can divert some parameters into good effects and some parameters into bad effects. So, this is the basic introduction of vibration. Similarly, the various terms used in vibratory motions are as follows. One is the periodic motion, second one is your time period, third is your cycle, fourth is your frequency, and then the last is your amplitude. Now, what is periodic motion? Periodic motion means a motion which repeats itself after equal intervals of time. So, after equal intervals of time, the motion is continuously repeating. So, such type of motion comes under the category of periodic motion. And the time taken to complete one cycle is your time period. Now, time taken to complete one cycle is the time period. So, in time period, there is one term, cycle. So, what is a cycle? Cycle means the motion which is completed during one time period. So, cycle time period are interrelated with each other. Motion completed during one time period is your cycle, and time taken to complete one cycle will be your time period. And under this cycle within the time period, okay, because of the vibrations due to the oscillations, the number of cycles per unit time is termed as what? Frequency. So, for frequency, number of cycles per unit time is needed, and for cycles in one time period, the motion which will be completed is being needed, and for time period to complete one cycle, what amount of time is taken is needed. So see, all these things are interrelated. The last one is your amplitude. Amplitude means the maximum displacement of a vibrating body from its equilibrium position. What will be the displacement of the vibrating body from its equilibrium or mean position? So, by considering the maximum displacement, we can determine the maximum amplitude of a vibrating body or a vibrating system. Now, the next one is your degree of freedom. In kinematics of machine also, we have studied about the degree of freedom, and we have determined the number of degree of freedom for number of mechanisms. Okay. Similarly, in vibration also, degree of freedom term is incorporated. Here, the degree of freedom means the displacement. How much displacement, how many displacements are developed in a system. So technically, the minimum number of independent coordinates required to specify the motion of a system at any instant is termed as degree of freedom. Here, there are three figures that you will see. This is your figure number one. For example, figure 1, this is figure 2, and this is figure 3. Now in figure number 1, a spring mass system, this is your mass and this is your spring. A spring mass system is shown and this is the displacement along x-axis. So here there is one displacement. Okay, so here degree of freedom will be 1. In second figure, there are two masses and two springs which are attached and it assembled to a complete two mass spring system. Here the degree of freedom will be 2. The displacement of mass m1 and m2 is constrained in one direction, but there are two displacement along mass m1 and along mass m2. So here the degree of freedom will be 2 displacement. And in figure number 3, a cantilever beam is shown, and in this cantilever beam, at a number of points, there are masses. Okay, so in here, the degree of freedom will be infinite because there are infinite masses which are shown in the figure. So in such conditions, when there are infinite number of masses, the degree of freedom will be infinite. So here the degree of freedom will be infinite. For this for this mass there will be some degree of freedom, for this mass there will be some degree of freedom. So for number of masses there will be number of degree of freedom and it may converge to an infinite number. So this is the concept related to degree of freedom. Generally you should concentrate on single degree of freedom and 2 degree of freedom. Now the most important term in vibratory motion is the simple harmonic motion, because with the help of simple harmonic motion, each and every frequency equation, natural frequency equation is derived. It is a very important equation for simple harmonic. So generally, simple harmonic motion means what? To and fro periodic motion of a particle about a fixed point. In this figure also you can see that there is a to and fro motion of a particle which is traveling from a positive phase to a negative phase in through a equal interval of time. So generally in such type of motion, acceleration is always directed towards the mean position, and also the acceleration is proportional to the displacement from mean equilibrium position. If there is a to and fro periodic motion about a fixed point where the acceleration is always directed towards the mean position and it is proportional to the displacement from the mean position, then such type of motion is termed as simple harmonic motion. And the expression for simple harmonic motion is x equal to x sine omega n t, where x is the amplitude, omega nt is the angle. Okay, now let us move towards the type of vibratory motion. So free or natural vibrations is one type, force vibration is another type, and the third is your damped vibration. Now, generally, what is free vibration or natural vibration? It means that if external excitation is applied on a body, an external force is applied on the body, and the body gets disturbed. And after the disturbance, if that external excitation is removed, then the system will vibrate on its own. Such type of vibrations comes under the category of free or natural vibration. So now you tell me, can you give me some example of free or natural vibration? Any one of you? Any practical example? Yes? Anyone? Any one of you? Harshit, Akhilesh, Mayur, Vibhor, Sanket? Can anyone give me the example of very simple? No one? So very good. Spraying. Now, for example, see, generally in dynamics of machine, there is a practical of spring mass system. You have performed that practical of spring mass system, and in that spring mass system, a spring is attached on a bracket, a vertical spring. And for example, if we will apply some external excitation on the spring and then we will release that external excitation, you will find that the spring will continuously up to a certain time period, it will elongate and then it will deform, elongate, deform in a elastic pattern. Okay. For example, the strings of the guitar, just strike the string and release your external excitation finger force. The string will vibrate. It is a free vibration. Force vibration means vibration under the influence of external force. So, for example, if we have attached a mass on a spring and then if we have pulled the mass and released the mass, so with the influence of that mass, there will be vibration in the system. And under this condition, the vibrations which are set up are known as forced vibration. The third one is your damped vibration. In example, shock absorbers. When there is a reduction in amplitude over cycle of vibration, dampers are used. So what happens in shock absorber? Generally, when the vehicle is moving on a bumpy road, okay. So what does shock absorber does? It dampens the vibration slowly under a period of time, and the amplitude of vibration reduces. So in damped vibration, slowly the vibrations are damped. Okay. So these are the three categories of vibration. Now let us move to the longitudinal vibration. What is longitudinal vibration? For example, see this figure. In this figure, this is your shaft and here this is your mass. there is a disk here, and this point B is your mean position. For example, this position is your mean position. This is your mean position. So generally what happens, take the example of a spring mass system. In a spring mass system, when we'll apply the force and release, the spring will elongate and it will deform. So what happens? The particles of that system which moves parallel to the axis of the shaft and the vibrations which are set up are known as longitudinal vibrations. In this figure, this is your shaft and this is your disk. So generally, when the particle of the shaft or a disk moves parallel to the axis, axis is vertical. When the particle moves parallel to the axis of the shaft, the vibrations which are set up are known as longitudinal vibration. Here, see, disk is elongated and it reaches to position C from mean position B. This is because elongation, hence tensile stresses will be developed. Similarly, the disk is deformed or it gets shortened after elongation and it reaches to a position A. So here there is shorten of the length. Here compressive stresses will be induced. So you can see that, for example, if this is your system, okay, and you are applying a force, so spring at one time spring will get elongate and at next position it will get shortened. So continuously due to elongation and due to elongation and due to shorten will be the correct word. Okay. Alternately tensile stresses and compressive stresses will induced in the shaft. So generally in a simple term I can define longitudinal vibration as a vibration where there is a elongation and shortening of the system which develops alternately and thus the stresses of tensile and compressive nature are induced in the system. In such type of vibrations, the particles of the system moves parallel to the axis of the shaft. The second one is your transverse vibration. In transverse vibration, what happens? The particles of the shaft or disk moves approximately perpendicular to the axis of the shaft. And if this condition is evolved, the vibrations which are set up are known as transverse vibration. Basically, here you can see that continuously, again, this is the same setup. This is your mass and mean position is B, and this is your shaft. So, what you can see continuously, the mass is subjected to one position and it goes to A, and again it moves to the another position with respect to mean position and it reaches to point C or position C, and B is your mean position. Okay. Now here you can observe that from this figure there is alternately bending of shaft, and if the bending word comes into picture, then here there will be bending stresses which are induced in the shaft, and these bending stresses will be tensile and in compressive in nature. So because of this bending or because of this bend in shaft, bending stresses will be induced. Now let us move to the torsional vibration. In torsional vibration, a twisting moment comes into the picture. This is my shaft. This is the mass which is attached at the one end of the shaft, and one end of the shaft is fixed. And if I will project it, the this disc is of circular cross section. Okay, this is your mean position. Now what we are doing, we are twisting the disc at a certain angle, for example theta. Okay, so disc is twisting. At one instant it will move here. Okay, then it will move here. So this will be the twisting movement. Okay, you have performed the practical. You have performed the practical related to the torsional vibration, that is your two rotor system, single rotor system, to determine the natural frequency of a single rotor system and a two rotor system. Here, am I audible? Am I audible? Okay, okay. Let us continue. Let us continue. Here, so we were dealing with the torsional vibration. In torsional vibration, there will be the twisting. For example, if this is your rotor, let us assume that this is your rotor. Okay, in this direction. So what we are doing, we are twisting it. So there will be this twisting, untwisting movement, and this is your shaft. Okay, so at one position it will twist, another position it will untwist. So this twisting and twisting movement will cause the torsional vibration. Here what happens? The particles of the shaft or disc move in a circle about the axis of the shaft. Similarly, the vibrations which are set up here are known as torsional vibrations. So let us sum up all these three vibrations. Okay. See, for example, this is your shaft. Okay, it is fixed. And if I'm applying a load, and let us assume it is for example, it is a spring, and here there is a load. And if I will pull the load and I will release, what will happen? This massless shaft will shorten and then it will elongate, shorten, elongate. And as a result of which, the vibrations which are set up are known as torsional vibration. Similarly, again, now what I will do, this again take the example of this shaft, it is fixed here. Now I will, like a pendulum, okay, I am twisting it and I am releasing. So what it will do, this is the mean position, it will bend here and then it will bend here. So this will be the position. So such nature comes under the category of transverse vibration, bending stresses are induced. And third is your torsional vibration. In torsional vibration, let us assume that at this end there is a disc. Okay, and what I am doing, I am twisting this disc. So because of this twisting, the shaft will also twist, the shaft will also twist, untwist. And because of this, torsional shear stresses are induced in the system. Okay, so these are the three types of vibration. So now let us move to the next part, method of vibration analysis. Now please listen everyone, that carefully, please carefully understand these three equilibrium methods. Okay, because these three equilibrium methods are very important. So all of you, all those students who are present here, please carefully see the process how to find the natural frequency of a system by using these three methods, because On the basis of these three methods, the gate questions are asked. It is a very important topic, vibration. You can say that blindly, I can say that minimum 4 to 5 or 6, 7 questions on the vibration topic comes. Minimum 5. You can see any paper of gate. Okay. So let us start. Method of vibration analysis. So after seeing the basic fundamentals of vibration, now we are moving to the vibration analysis concept. Now, the first method is the equilibrium method. And what the equilibrium method says, whenever a vibratory system is in equilibrium, the algebraic sum of forces and moments acting on it is zero. It is based on D'Alembert principle. The algebraic sum of all forces and moments acting on a system will be zero whenever the system is in equilibrium. So basically, equilibrium method, then your energy method, then your Rayleigh's method, all these three methods are used to determine the natural frequency of a system. Okay, so now let us start. So here there are three figures. As you can see, there are three figures. This is figure number A. This is my figure number B. And the third one is figure number C. Now what I have done, we will go step by step. In the first figure, you can see that a spring is attached. Okay. On one end it is fixed and other end is free. So it is its equilibrium position. The section AA is equilibrium position. Now what we are doing, this end is free and this end is fixed. So it is your equilibrium position. Now in second figure B, what we have done, we have attached a mass on the free end of the spring. So when we will attach the mass, the spring will get elongate. And when the spring will get elongate, so the position, equilibrium position, which was AA in figure number A, will be changed to position BB. I have just attached a mass, nothing else. And due to the weight of this mass, because of this weight, because this mass will have some weight, that is W equal to mg, the spring will get elongate. And here you will get the deflection. Now the position AA is changed to position BB and let this deflection be what? Delta. Okay. Now generally what happens when, because of this mass, if the spring gets elongate, because of this elongation, a spring force or a restoring force will be developed on the spring. Restoring force means what? It will try to move the mass to its equilibrium position. Okay. So, because of this weight which is attached on the spring, a equal and opposite a restoring force will be developed on the spring. This is my restoring force. Okay, restoring force is also known as spring force. And this spring force is K into delta and its direction will be opposite to the mass. Now basic. Basic is what? What is stiffness? What is stiffness? Stiffness is defined as load per unit deflection. So what will be the load? Load will be stiffness into deflection. So this load is nothing but your restoring force or a spring force. Now, so this is your second figure B. Now, if I will create a free body diagram of figure A, this is the free body diagram of figure B. So in your free body diagram, this is my mass. On downward, this is mg, which is equal to weight, and upward only one force k delta. So this is free body diagram. And under static equilibrium condition or position, upward force will be equal to downward force. Okay, so mg will be equal to k delta. Or simple, if we will apply the equilibrium condition, summation f of y equal to 0. Okay, so plus k delta minus mg equal to 0. So k delta equal to mg. You can also use that condition also, or in simple concept, upward equal to downward force. So upward force is only one, okay, and downward force. So downward force is mg, okay, and upward force is what? K delta. Downward force is mg. This is your downward force, and this is your upward force. So mg is k delta in figure number 2. Now go to figure number 3. In figure number 3, what I have done, I've again, by using some external excitation, okay, I've again pulled this mass. So what will happen? If I will pull this mass, the mass is again deflected. And if the mass is deflected downward, it means that through a distance x, it is displaced through, again it is displaced through a distance x. If it is displaced through a distance x, the displacement will be in downward direction. If the displacement is in downward direction, it means that the velocity will be in downward direction. And if the velocity is in downward direction, then the acceleration will also be in downward direction. Okay, x double dot acceleration, x dot velocity, and this is the displacement. Now, here from this point, this is the mass, W equal to what? Mg. So if the mass is displaced downward, okay, so due to the displacement, a spring force or restoring force will be developed. So what is spring force? It is, you tell me. Students, anyone unmute yourself and tell me here what will be the spring force? Yes, and its direction will be upward. Tell me, anyone? Spring force is what? Stiffness into deflection. So stiffness is K. And what is the deflection now? From mean position, the total deflection is what? Total deflection is x plus delta. If we are referring this mean equilibrium position AA, so at mean equilibrium position BB, the deflection was delta, and at mean equilibrium CC, the total deflection will be x plus delta or delta plus x. So restoring force will be delta plus x, and its direction will be upward. Why upward? Opposes the displacement and weight. Similarly, as the accelerating force, because acceleration is downward, the accelerating force will be downward, and if the accelerating force comes into the picture, then there will be an inertia force. And what this inertia force will do? This inertia force will act opposite to the accelerating force. So the inertia force will be, this is your inertia force, and this inertia force will be m into x double dot, and its direction is upward. Now see, here in this two, in figure B and figure C, you can ask me a question that, sir, in figure B, why there is no inertia force? Because in figure B, we have just attached a mass. We have not pushed that mass. We have just attached the mass, and because of the weight of the mass, the position of the system is transferred from AA position to BB position. But in figure C, we have applied an external force, we have given an external excitation. Actually, what we have done, we have pulled the mass to a distance x and then we have released it. Okay, when we will pull the mass, okay, the displacement will be increased. So the displacement is x plus delta, and same as a result of which the inertia force will be developed in the system and it is mx double dot. So now the free body diagram here, this is the free body diagram of figure B. In this free body diagram of figure C, this is my mass block. Okay, downward will be W equal to mg, and upward there will be two. One will be your restoring force and another one will be your inertia force. Okay, now, so if we will use the D'Alembert principle, it says that the algebraic sum of all the forces acting on the system is zero. So vertically upward positive mx double dot plus k delta plus x, and mg is downward, so minus mg equal to what? Zero. Then sorry, mx double dot plus open the bracket k delta plus kx minus mg equal to zero. Similarly, see mg equal to what? K delta. In second figure, in free body diagram, figure number B, here you have seen that here mg is equal to what? K delta. So K delta and mg will get cancelled. So my equation will be mx double dot plus kx equal to 0. If I will take m as common, then it will be x double dot plus k by m, x equal to 0. So this is the, after taking m as common and then substituting it, we will get this final equation, that is x डबल डॉट प्लस यहाँ पर m नहीं था तो डिनोमिनेटर में k by m into x, and this m will be transferred here 0 by m, then by default it is 0. So now what we have to do, students, see this midterm, this is what? K by m, and see the standard equation of simple harmonic motion. The standard equation is x double dot plus omega n square x equal to 0. So if I will compare this equation with my standard equation, and if I will compare the coefficient of x, so here it is omega n square in equation 2, and in equation 1 the coefficient of x is what? K by m. Okay, so now I can say that the natural frequency is k by m under root. So this is the expression for natural frequency using equilibrium method. Understood? This is the basic. Now, for example, as as I have told you, as natural frequency equal to what? K by m. First thing, I can write this equation as k multiplied by g upon m multiplied by g. Okay. Similarly, I can say that this is my kg and mg is what? K into delta. Mg is what? K into delta. Okay. I was just checking that any entry has to be admitted. Okay. Now, which is equal to, this will be equal to what? Kk gets cancelled and it will be G by delta. So natural frequency can also be written as G by delta. This is another equation of natural frequency. Similarly, what is time period? Time period means one cycle of motion completed in an angle 2 pi. This is your time period. So, time period will be 2 pi by omega n, which will be equal to 2 pi. I can write omega n as k by m. Okay, which is equal to 2 pi m by k. So this is for time period. And I have told you one cycle of motion is completed in an angle 2 pi. This is your time period. Okay. Similarly, natural frequency Fn is the reciprocal of what? Time period. So, if it is the reciprocal of time period, I can directly write as 1 by 2 pi under root k by m. This is the natural frequency of equilibrium method related to a spring mass system. So now we have completed natural frequency omega n, that is in radian per second. We have completed natural frequency, okay, in hertz, and similarly we have completed the concept related to equilibrium method. Now let us move to the another method, that is your energy method. First is your equilibrium method. Second one is your energy method. Now in energy method, the energy method says that in a conservative system means what? A system with no damping. In a conservative system, the system which has no damping, the total energy is your mechanical energy. So the total energy, that is your mechanical energy, and involves it involves mechanical total energy. In terms of mechanical energy involves the sum of kinetic energy as well as potential energy, and it will remain what? Constant. So let us see the energy method concept. Now, energy method says that total energy is constant. Total energy is your kinetic energy and potential energy. Now, what is kinetic energy? Kinetic energy means energy possessed by a body by virtue of its motion. And potential energy means energy possessed by body by virtue of its position. So in kinetic energy, there is the motion. Motion means there is a velocity. And in potential energy, there is a position. Position means your displacement. So for example, kinetic energy is half mv square. Okay. So here I have replaced velocity with x dot square. Okay, velocity is replaced by x dot. In vibration, we represent velocity by x dot, acceleration by x double dot. Okay, not VNA. So here, this is my spring having stiffness what? K, and here there is a mass. Okay, it has displacement x, and the system is in static equilibrium. Now, potential energy is product of mean force into displacement. So mean force means initial force under static condition, it is 0, plus spring force kx by 2 into displacement will be x. So the answer of potential energy will be kx square by 2. This is our basic potential energy equation, kx square by 2, and kinetic energy half mx that square. Okay. Generally, basically, we have studied potential energy as mgh. Okay. Here, this mg is replaced because it is a spring system. Na? So, this mg is replaced by your spring force, mean spring force, and h, that is the height, is replaced by your displacement x. Now, after this, as per the method, it says that sum of kinetic energy and potential energy remains constant. So if I will differentiate with respect to time, the total energy, and the total energy is your kinetic energy plus your potential energy. Okay, so it will be equal to what? 0. So let us substitute d by dt. Kinetic energy is half m x dot square plus potential energy is half k x square. It will be equal to what? 0. Now, here the equation will be 1 by 2 into m into 2x dot x double dot plus 1 by 2 k 2x into x dot, and it will be equal to what? 0. 2 get cancel, 2 get cancel. So from here we will get the equation m x double dot plus k into x, and x dot will be common. It is equal to 0. So I can write this equation as x double dot plus k by m into x, which is equal to 0. And my simple harmonic motion equation is what? X double dot plus omega n square x equal to 0. So here coefficient of x is k by m. For example, this is equation number 1 and this is equation 2, and here the coefficient of x is omega n square. If I will compare the coefficient of displacement from equation 1 and 2, I can write omega n square equal to k by m. So omega n will be what? It will be under root k by m. So this is the expression for natural frequency through the energy method. Now the third method is your Rayleigh's method. So generally, what is a Rayleigh's method? It is an extension. It is an extension of energy method. And this method says that there will be a constant interchange of energy between potential energy of the spring and kinetic energy of the mass while the system executes a cyclic motion. So during the execution of cyclic motion, continuously there will be the interchange of potential energy and kinetic energy. Potential energy and kinetic energy. Similarly, in this method, the maximum kinetic energy at mean position. When there will be maximum kinetic energy? At that point where potential energy will be zero, will be equal to the maximum potential energy, that is your strain energy at extreme position. And maximum strain energy or maximum potential energy will be developed when kinetic energy at that point will be zero. So the kinetic energy maximum is equal to potential energy maximum equal to total energy of the system. Now here let us see that, for example, for example, vo- voice is properly audible. Harshal, Vibhor, Mayur, Vishal, Ashu, voices. Am I audible clearly? Okay.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes. Okay then. Let us continue. So here, as the release method says that there will be a constant interchange of energy between potential energy of the spring and kinetic energy of the mass while the system executes cyclic motion. So now let us see that if maximum kinetic energy will be equal to the maximum potential energy, and that is the total energy of the system. Here let us assume that let the motion be simple harmonic. Let the motion be simple harmonic. Also, if the motion is simple harmonic, that let the displacement be x sine omega and t. And if I will differentiate this displacement, okay, with respect to time, I will get what? Velocity. So velocity will be x omega n cos of omega n t. Okay, and if I will differentiate this velocity with respect to time, I will get x double dot, that is the acceleration. But there is in potential and kinetic energy, only velocity has to be used. There is no need of acceleration, so we will not differentiate. Now, as kinetic energy of the system, we have seen it is half m x dot square. Okay, so let us substitute half m instead of x dot capital X. So it will be x square, then omega n square, then cos square omega n t. So this is the expression. Okay. So basically this cos square omega n t is approximately equal to 1. This angle is approximately equal to 1. So my kinetic energy will be half m x square omega n square. This is my kinetic energy. Now let us see the potential energy. As potential energy is half k x square. So half K, instead of x, I will write x square sine square omega n t. Here also, 1 minute. Here also, this value is 1. Very so, my potential energy will be 1 by 2 k x square. Okay. Now what we will do? Here, as the question says that kinetic energy maximum is equal to what? Potential energy maximum. So kinetic energy maximum will be half m x square omega n square, and potential energy will be half k x square. If this is the condition, then 1 by 2 get cancelled. X square get cancelled, and we get omega n square equal to k by m. So omega n will be what? It will be k by m. Understood? So here what we have seen, now we have we have discussed the three methods. One is your energy method, one is your equilibrium method, and one is your Rayleigh's method. And all these three methods are used to determine the natural frequency of the system. So from all these three methods, we can conclude that the natural frequency is omega n equal to under root k by m. Either we use equilibrium, or we use energy, or we use Rayleigh's method. For a free system, free spring mass system, the energy natural frequency is under root omega n equal to under root k by m. So after this, let us move to the next part, and that is your natural frequency of transverse vibration. As I have told you, in transverse vibration, when the particles of shaft or mass are perpendicular to the axis, then transverse vibration is set up. And in transverse vibration, there is continuously what? In transverse vibration, there is alternately bending from one mean position to the another mean position, that we have seen. Now bending stresses plays a role in transverse vibration. See, in this figure there is a cantilever beam. Okay, it is fixed to the one end, and a mass W is attached at the free end. As you can see, if I will displace this body from the mean position, okay, it will alternately bend. Now let us try to draw the line diagram. For example, see, this is your cantilever. Okay, this is your shaft, and this is your mass. At one instant, as it is a transverse vibration, the position will be similarly at one instant. The position of mass will be here. Okay. Now, for example, let this be the length of the shaft. Now tell me, what is deflection? In mechanics of material, in deflection of beams, for a simply supported beam fixed at one end and free at the other end, and there is a point load, what is the equation for deflection? W L Q upon 3 EI. This is the basic expression for deflection. Okay. Now, as what is stiffness? Stiffness is load per unit deflection. Okay. So W upon deflection is W L cube upon 3 EI. So here 3 EI upon L cube. This is the expression K equal to 3 EI upon L cube, important expression. Now, as natural frequency is what? Natural frequency is omega n upon omega n equal to under root K by M. So here, instead of K, I can write what? I can write 3 EI upon L cube, and there is M. So this will be the expression. ये बन गया आपका expression. Now, also we have seen that we have also seen that what is omega n? Omega n is what? G by delta. Okay. So G upon delta is what? W L cube upon 3 E I. Similarly here, I can say 3 E I G, and at the denominator it will be what? W L cube. W is what? Mg into L cube. Okay. So Gg gets cancelled. So omega n equal to, here G and G get cancelled. So omega n equal to 3 EI upon M L cube. So from this expression also, omega n equal to under root G by delta, we can determine the natural frequency of transverse vibration. Now similarly, let's go to the natural frequency for torsional vibration. Here, in natural frequency for transverse vibration, see, this is your shaft, massless shaft. This is your disc. Okay. This is the length of the shaft. For example, from this center, let this point be A. So OA is the mean position, and what we are doing, we are giving From this OA position, let a angular twist of angle theta, this is your theta, let theta be the angle of twist. So at a certain point, the when I will rotate the disk through an angle theta, let us assume that it reaches to a point, see, let this point be A dash, and this angle is your theta. Okay, so we have considered a shaft of negligible mass whose one end is fixed and other end is carrying a disk. Now what we are doing? If the disk is given a twist about the vertical axis, okay, and then released, so what will happen? If we have twisted the disk and released, the disk will start to oscillate about the axis and will perform some torsional oscillations. Okay, so what we have done, we have twisted the disk through an angle theta and released. So the disk is oscillating with respect to the vertical axis. Here, theta is what? Theta is the angular displacement of the shaft from mean position after time t. M is the mass of disk. I is the mass moment of inertia of the disk. K will be the radius of gyration. And Q will be the torsional stiffness of the shaft. So now at any instant, the torque acting on the disk are, there will be two torque. One will be because of the angular displacement, inertia torque will be developed, and here inertia torque will be I into theta double dot. And second one will be your restoring torque. In spring there is a restoring force, but where the torque comes into the picture, so instead of restoring force, here there will be a restoring torque, and the restoring torque is q into theta. So under equilibrium, both will be, sum of both the torque acting on the disc will be equal to 0. So for equilibrium, the sum of all torques acting on the disc must be equal to 0. So it means that the two torques which are acting on the body, one is your inertia torque I theta double dot, and another one is your restoring torque q into theta. So the summation of these two torque will be equal to 0. So from here I can say that I will write here theta double dot plus q by I into theta will be equal to 0. Okay. And what is the standard simple harmonic equation? X double dot plus omega n square x is equal to 0. So if I will compare the coefficient of the displacement x and the coefficient of angular displacement theta, I will write as omega n equal to q by I under root. Okay, so this is the expression omega n equal to q by I. Now, for example, I have to add one more slide here. Okay. Now, see, in the previous equation, we have seen that inertia torque plus restoring torque. These are the two torques which are acting on the system. Now, so from here, theta double dot plus q by I, theta equal to 0, and if we have compared it with the standard equation, it is omega n q by I. Okay, so here this is our equation. Now see students, tell me the torsional equation. What is the torsional equation? As torsional equation is T by what J equal to Q by R equal to G theta by L. This is the torsional equation. Okay, don't get confused. I will write this Q as tau. Tau, Q, sigma S are the shear stresses. Now here, this T by, I can write T by theta equal to G into J divided by L. I can write this. And here T by theta is what? It is the ratio of twisting moment with respect to the angle of twist. So this ratio T by theta, twisting moment to the angle of twist, is your torsional stiffness. Okay, and this is your Q, torsional stiffness, and this torsional stiffness is Gj divided by L. So now what I can do? Now omega n equal to, instead of Q, I can write G into J upon I is already there into L. So this is your equation. Okay. And as what is natural frequency? 1 upon 2 pi q by I. This is your natural frequency. So I can write Fn equal to 1 upon 2 pi, instead of q, G into J divided by I into L. So this becomes your natural frequency. Okay. So from here you have seen how to derive the natural frequency in terms of omega n and in terms of Fn for a torsional vibration system. Now let us move to our next topic, that is your spring in series and spring in parallel. Very important. Now in spring in series, let us see the expression equivalent length. The basic aim in this topic is to derive the equivalent spring stiffness equation for spring in series. So see here, one end of the spring is fixed, okay, and one end is free. Here there are two springs. For example, this has stiffness K1 and this has stiffness K2. This is your spring 1 and this is your spring 2. Okay, so spring 1 having stiffness K1 and spring 2 having stiffness K2. At the one end there is a mass attached. Okay, and displacement is in downward direction. So here, as both the springs are attached in series in line, okay, so there will be the total deflection, and the total deflection will be x1 plus x2. So here let x be the total deflection of the spring, and total deflection will be deflection of x1 plus deflection of x2. So total deflection will be x equal to x1 plus x2. Similarly, let K equivalent, KEQ be the equivalent spring stiffness? We know that stiffness is load or force per unit displacement or deflection. So displacement will be force per unit stiffness. So if I will assume it as our mother equation, so force upon K equivalent will be force upon stiffness in spring 1 plus force upon stiffness in spring 2. Here F is common. Why F is common? Because each spring carries same load F. So if F is common, F will get cancelled. So here F is get cancelled. And if F is get cancelled, your equation will be 1 upon K equivalent equal to 1 by K1 plus 1 by K2. So this equation represents the equivalent spring stiffness equation when the spring in series. Okay, and with the help of this equation, we can determine the stiffness of equivalent spring also. We can determine the stiffness of spring 1 and we can determine the stiffness of spring 2. Only uh, thing is that the springs should be in series arrangement. Okay. Now let us see the spring arrangement in parallel. Here also you can see that there are two springs. This is your spring number 1 and this is your spring number 2. Spring number 1 has stiffness K1, spring number 2 has stiffness K2. Okay, X1 is the displacement of spring 1, X2 is the displacement of spring 2. Here there is a mass, so the total displacement will be what? X. Now, here we can see that the deflection is same in both the springs. Why deflection is same in both the springs? Because both the springs are attached in parallel. So if the mass is attached to both the spring and if there will be a total displacement, so the displacement of x1 and displacement of x2 will be same as they are all identical. Now deflection is same in both the springs. It means that x1 and x2 is same. Similarly, the weight share by K1 spring will be K1 into X because the basic is W by X. So what will be W? W will be K into X. So the load share by K1 spring will be W1 into X and load share by K2 spring will be W2 into X. So load share by spring 1 will be W1 into X and it will be W2 into X. 1 minute. Load share will be W1 equal to, it will be W1 equal to K1 into X and W2 equal to K2 into X. Okay. So this is W1 load share by spring 1. This is W2 load shared by spring 2. Now equivalent spring stiffness. So as W is what? K equivalent into X. So I can write K1 into X plus K2 into X. So K equivalent into X equal to K1X plus K2X. Displacement is same. So here the expression will be K equivalent equal to K1 plus K2. So with the help of this equation, we can find out the equivalent spring stiffness for spring in parallel. So these are the two. This is the spring in series and this is expression is spring in parallel. Okay. Now the last topic is the critical or whirling speed of shaft. Now basically what is critical speed or whirling speed? So the speed actually, let us see here in this diagram. The speed at which the shaft vibrates violently is known as the critical speed or whirling speed of shaft. In dynamics of machine practical also you have seen the whirling practical where we are determining the whirling speed of the shaft. You have seen that the shaft is continuously it is vibrating, okay, because of the eccentricity. So basically what happens, see, this is your rotor having mass m and this is the your shaft axis, okay, and here this is one bearing and here there is another bearing. So system is like this. Now generally what happens, the eccentricity of the mass does not coincide with the axis of the shaft. You can see here this is the CG, this is the CG of the rotor and this is your shaft axis. So this CG is not coinciding with the axis. It is somewhat eccentric. Okay. So when the shaft rotates, for example, this is your, these are your bearings. Okay. And here, this is your rotor. This is the axis of the shaft. So somewhat the CG of this rotor is eccentric. And if this condition arises, when the shaft will rotate, okay, so because of this eccentricity, centripetal force will be developed. Centrifugal force, sorry, not centripetal, centrifugal force will be developed. And the direction of centrifugal force will be towards this eccentricity. Okay. And because of this disturbance of centrifugal force, the deflection of shaft will be towards the eccentricity and the shaft will vibrate violently. And because of this violent behavior of the shaft and due to the cumulative tendency of the centrifugal effect due to the rotation, the shaft will fail at one point. Okay. So the speed at which the shaft tends to vibrate violently in the transverse direction is known as the critical speed or whirling speed. Similarly, the speed at which the shaft runs so that the additional deflection of shaft from the axis of rotation becomes infinite, then it is known as critical or whirling speed. So in these two figure, this is the stationary figure. In figure A, in figure A, this is your stationary, this is the axis of rotation of shaft, and this is your eccentricity, and they are displaced at E. In figure number B, when shaft tends to rotate, see, you can find that from this axis, the eccentricity was E. Okay. Now, as because of this eccentricity, centrifugal force is created towards the eccentricity side, and the shaft tends to move towards that eccentricity side. When the shaft was horizontal, there was no displacement y. But because of this eccentricity and because of this eccentric position, through the rotation and because of the centrifugal force, the shaft is bending towards the eccentricity. So from this position, it has created a displacement y. So this additional displacement is created. So from this eccentricity point, this distance is E. Okay, when shaft was stationary, now the total deflection will be Y plus E. And this Y is the displacement due to the centrifugal force. So now you can see that because of this speed, additional deflection of the shaft from the axis of rotation and it will become infinite. As the speed will goes on increasing, this displacement will increase. So, and at one point the shaft will fail. So this is the concept of critical speed or whirling speed of shaft. Here critical or whirling speed is the same as natural frequency of transverse vibration, but its unit will be revolutions per second. The expression for critical speed is nc equal to 1 upon 2 pi g by delta, and if I will substitute the values, it will be 0.4985 upon root delta, but its unit will be in rps, not in rpm. Okay, now let us see this figure and try to solve the question. Here you can see that there is a cantilever type of a beam. One end, at one end it is fixed at pivoted point O, and at the other end it has a mass, and that point is P, and also at point Q there is a spring which is attached. Okay, and one end of that spring is attached to the rod and other end is to the fixed end. Now there are four options A, B, C and D, and we have to determine what? We have to determine the frequency of the vibrating system. Now in this question, as let us draw the free body diagram. This is the free body diagram of the system. For example, if the system, this total beam length is 2a, okay. If the position is displaced from point P to P dash, so this will be the deflection, and this deflection will be what? If this is the, if we are assuming this angle as theta, so this deflection, if we will find this deflection, it will be chord length, that is twice a into theta, twice a into chord length. For example, like this is theta and this distance is x, so this will be x to theta. Okay, so this is twice a into theta at this point. Similarly, a spring is attached, it means that there will be a restoring force. अगर स्प्रिंग लगा है तो यहाँ पर रिस्टोरिंग फोर्स आएगा. ओके, सो देर आर टू फोर्स. Because of the attachment of the spring, there is a restoring force. Distance is given, so it will be in terms of torque, and because of this displacement there will be an inertia torque. Okay, so restoring force will be equal to the negative inertia torque. Why negative? Because both are in opposite direction. I can also write this equation as restoring torque by using the D'Alembert principle, that summation of all the torque, restoring torque plus inertia torque, will be what? Equal to 0. I can also write like this. Okay, by applying the D'Alembert principle. Now, let us find the restoring torque. So, what is restoring torque? Now, you will see basically restoring torque is, this is stiffness K, and at the center, if this is displacement X, so here, if this is at the center, this displacement will be what? X by 2. So restoring torque will be K into X by 2 and multiply with respect to this fixed point. So from the center, this distance is A. Torque is force into displacement. This distance is A. So K into x by 2. This is your force multiplied by this is your torque multiplied by the distance. Restoring force into distance is A. Okay. But here K into x is what? X is twice A theta. So here I can write instead of x twice A theta by 2 into what? A. 2 get cancelled. So restoring torque will be A into A square K theta. Similarly, what will be your inertia torque? Inertia torque is your I into theta double dot. Okay. For this disk, the mass moment of inertia will be ml square into theta double dot. ml square is the mass moment of inertia. Now what is length? Length is twice A. So instead of L, I can write twice A the whole square into theta double dot. So it will be 4A square m into what? Theta. Okay. So this is your inertia torque. Now let us see the condition. Restoring torque plus inertia torque. Inertia torque is how much? Restoring torque is your A square K theta plus inertia torque is your 4 A square m theta double dot which is equal to what? 0. Okay. A square can be common. If A square is common, here it will be. I can write this equation as K theta plus 4m theta double dot equal to 0. Also, I can write this equation as first I will write the acceleration theta double dot plus then I will write for example 4m theta double dot plus k theta equal to 0. This can be written as theta double dot plus k by 4m into theta equal to 0. This can be written as this is the k by 4m. This is the your equation. So as compared with the as simple harmonic equation is what? Simple harmonic equation is x double dot plus omega n square x equal to what? 0. So omega n square will be I am comparing the coefficient of x with theta. So it will be k by 4m. Okay. So from here omega n will be what? Under root k by 4m. So this implies Fn will be 1 upon 2 pi k by 4m. This is your equation. Okay, so this is the this is the frequency. So Fn 1 upon 2 pi k by 4m. Fn 1 upon Fn 1 upon 2 pi k by 4m. So this is your option. It is for 2 marks. Now here I have directly, it is a 1 mark question. A mass is attached to the two identical spring. So see, this is your mass which is attached to identical spring. Okay, and these springs are in parallel, and we have to determine the frequency for a single degree of there will be only one displacement. We have to determine the natural frequency. Okay, so it is there are four options. So simple C. This is the spring in parallel. Arrangement is spring in parallel. And for spring in parallel C, for spring in parallel it is K equivalent equal to K1 plus K2. So equivalent stiffness will be K1 plus K2. Here see K1 is equal to K and K2 is also K. So K1 equal to K and K2 will be also K. For example, this is spring 1 and this is spring 2. So both has stiffness K. So it will be K plus K. So it will be K equivalent will be twice K, which is written here. And what is omega n? Omega n is K by m. So instead of K, substitute K equivalent, and K equivalent is what? 2K. So here instead of K, I am substituting here twice K equivalent. Okay. So 2K by m. So this is your answer. Very simple, 1 mark. See just the basic, nothing else. Now in this question, a spring mass system is shown in the figure and it consists of a block of mass 5 kg connected to a spring through a massless rope passing over pulley of radius r and mass 20 kg. Okay, the spring constant K is 1500 Newton per meter. If there is no slipping of the rope over the pulley, the natural frequency of the system is. Important question. Such type of questions every time they asked in GATE exam. Okay, see, I will explain you it in a very detailed and precise way. Generally, if you will see this figure, okay, here there is a mass. This is your mass. Okay, this is your pulley, and this is your spring. Okay, now for example, the system shown in the figure consists of a block of mass 5 kg. So mass is how much? 5 kg. So let small m be the mass of block. It is 5 kg. Connected to a spring through a massless rope passing over a pulley B of radius r. So radius of pulley is small r and mass of pulley. So let capital M be the mass of pulley. Okay. Small m is the mass of block and capital M is the mass of pulley. Then the spring constant. This is your spring. So stiffness is given. Stiffness is 1500 Newton per meter. This stiffness is given. And we have to determine what? We have to determine the frequency. काय में निकालना है? Radian per second. So we have to determine frequency of the system in radian per second. Okay, omega. So as I've told you, what? There are three methods. One is equilibrium method, one is energy method, and third one is your Rayleigh's method. So by applying any of this method, you can find the natural frequency of this spring mass system. Okay. So let us see two concepts. I'm using the energy method. Okay. And energy method says that total energy equal to constant. Total energy means kinetic energy plus potential energy. Why I am using energy method? Because see here there is a spring, okay, and also if there is a spring, potential energy will be developed, and as there is a block, and if the block is moving in radial in a linear direction, there will be kinetic energy, translatory motion, and if the pulley is rotating, there will be kinetic energy, rotational. So listen very carefully. I am what is the energy method? See here, energy method means what? Energy method says that sum of kinetic energy and potential energy remains constant. Okay. So what I am doing here, see, I am applying एनर्जी मेथड एंड बिफोर अप्लाइंग द एनर्जी मेथड यहाँ पर आप देखो फॉर एग्जांपल लेट अस चेंज द कलर सी let us assume that if this mass or this block A is displaced at a distance x from its mean position like this इसको मैंने खींचा if I pull this block the block is in this direction okay so here there is a displacement x and this will be your A dash understood I have pulled this block you I have pulled this block okay downward now for example this is B this point is B now tell me if I will pull this block downward okay the point B will move towards right because pulley will rotate and if pulley will rotate the rope will move so at that point this when block A moves to A dash this point B which is on the pulley it is moved to B dash and if it moves to B dash let this be the angle theta through the angle theta it is moving and if the point B is moving to B dash the spring will expand as a result of which here there will be restoring force which will be developed audible hello students hello yes sir okay lucky now okay so now let us go to the solution in this solution the total energy of this system will be total energy of system will be see this block A moves to position A dash because I have pulled it okay so there will be translatory motion this is your translatory motion so here there will be kinetic energy which will be developed because of this motion and that will be your translatory okay plus the pulley is also rotating from point B to B dash it has moved through a certain angle theta so again there will be angular so here kinetic energy will be developed and it will be rotational plus because of this spring here there will be potential energy okay so I am writing देखो इधर because of this block here there will be kinetic energy rotate translatory. ब्लॉक नीचे मूव कर रहा है ना, ट्रांसलेटरी मोशन. पुली is moving, so here there will be kinetic energy and it will be rotational due to the rotation of the pulley. There will be kinetic energy due to the translatory motion of the block. There will be kinetic energy due to the rotation of pulley, and there will be potential energy as the spring is attached. So these are the three energies, two kinetic and one potential energy. Now total energy, let us see the expression. Total energy equal to kinetic energy half m instead of v. Here it is half m, displacement is x, so velocity will be x dot, plus kinetic energy rotational, so it will be half, it is rotational, so mass will be replaced by mass moment of inertia and angular velocity will be replaced by linear velocity will be replaced by angular velocity. So it is half I theta dot square. See, in linear, in translatory, m into x square, that is m into v square. In rotational, mass is replaced by mass moment of inertia, and your velocity, linear velocity, is replaced by angular velocity. Plus, potential energy is what? Half k x square. Okay, so this is your basic equation. Now, here what we have to do? Now, tell me, as I can write like this displacement x is equal to r into theta. जितना ये डिस्प्लेसमेंट नीचे आया है उतना ये पॉइंट बी से बी डैश जाएगा, तो ये जो डिस्टेंस है, दिस डिस्टेंस, इट इज आर्क बी बी डैश. इसको और थोड़ा सा डिटेलिंग में लिखूं तो इट इज लाइक दिस. सी लेंथ ए डैश, दिस लेंथ ए टू ए डैश, ओके, यहां से लेके यहां तक इज इक्वल टू व्हाट? आर्क BB dash. Length AA dash is what? X. And arc BB dash will be, this is theta and radius is r. So this will be r into theta. If this is r into theta, then velocity will be x dot equal to r theta dot. Now what we have to do? We have to substitute all these values, okay, and we will differentiate it with respect to time. We will get an equation, we will substitute the values and we will get the answer. So let us substitute. So here we will write, the equation was like this. What? That total energy equal to half m x dot square plus half I theta dot square plus half k x square. Okay, as x equal to r theta, x dot will be r theta dot. Okay, now total energy will be half m, instead of x dot, what I will write? R into theta. It is x dot square. So it will be what? It will be r square theta dot square plus half I theta dot square plus half k. X is what? R into theta. So it will be R square theta square. This is total energy. Now we will apply energy method. Applying energy method. If we will apply energy method, so d by dt of total energy equal to what? 0, constant. So now let us differentiate d by dt half m r square theta dot square plus half I theta dot square plus half k r square theta square, which is equal to 0. Okay, now differentiate it. So while differentiating, it will be half m r square twice theta dot theta double dot. Then it will be half I twice theta dot theta double dot plus half k r square twice theta into theta dot, which is equal to what? 0. So from here, 2 get cancel, 2 get cancel, 2 get cancel. So m r square theta dot theta double dot plus I theta dot theta double dot plus k r square theta theta dot will be equal to what? 0. Okay. Now what we have to do? See here, in these two terms we can take acceleration as common. Okay. So this will imply mr square plus I. Here we will increase one step so that you will not get confused. First do one thing, take the angular velocity, okay, common. So if I will take the angular velocity common, it will be mr square theta double dot I theta double dot plus k r square theta, and here theta dot will be common. Okay, यहाँ से theta, from here theta, and from here theta. Now what I will do, I can write this equation as mr square theta double dot plus I theta double dot plus k r square theta equal to what? 0. Now from here, if I will take theta double dot as common, okay, so it will be what? M r square plus I, here it will be theta double dot common, and here it will be k r square theta, which is equal to what? 0. Okay. Now, so after this, I can write, see, the last term was mr square plus I theta double dot plus k r square theta equal to what? 0. So I can write theta double dot as, if I will take mr square plus I term as common, okay, अगर मैं एम आर स्क्वायर प्लस आई को कॉमन ले रहा हूं तो इट विल बी के आर स्क्वायर अपॉन एम आर स्क्वायर प्लस आई, like this. So now I can write theta double dot plus k r square upon m r square plus I into theta equal to 0. So see what I have done. Actually this m r square plus I have taken common. And if it is taken common, I can write like this. Okay. Now, so here, what is the simple harmonic equation? It is x double dot plus omega n square x equal to what? 0. So if I will compare, okay, the coefficient of theta and x, so it will be omega n square equal to k r square upon m r square plus I. Okay, and omega n will be what? K r square plus m r square plus I under root. Okay, here note that mass moment of inertia is half m r square for pulley. So r square get cancelled. So omega n will be k m plus, or do one thing, first substitute. First we will substitute all the values. K r square equal to m r square plus I. So since I is what? Half m r square. Okay. So I can write omega n equal to k r square upon m r square plus I is half capital M r square. Okay. So here this equation will be k m plus 1 by capital M. Stiffness is 1500, small m is 5 plus half, capital M is 20. So from here we will get omega n as 10 radian per second. So students, these were the some problems that I have explained you. Okay, just for your practice purpose. Likewise, if I'm frankly speaking, if you have developed the tendency of making the frequency equation, just go through the equilibrium method, Rayleigh's method, and your energy method. Generally, energy method and equilibrium method is sufficient to solve any type of the spring mass system problem for finding the natural frequency. And also, you have seen the concept related to spring in series and spring in parallel. Okay. So only in this concept you can solve the problems of free vibration. So that's from my side. If you have any questions, please ask me. You can freely ask me now. Or if there is any doubt, you can WhatsApp me. You know my email ID as well as my contact number related to theory of machine. So this is from my side. So now can we end the class? Vishal Fulzule, Ankit Chaure, Ayush, can we end the class now? Okay. Thank you. Thank you for your cooperation, for listening me. Thank you.